That's a really good question.
I mean, are there any challenges that you're facing right now with the work? Or I can imagine when it first started, there was probably many challenges. Like maybe take me back to right when you first started Virtual Flow. What were some of the problems or challenges at that time?
So, yeah, that's a good question. So when I started to develop Virtual Flow, I had no idea on how to best make this work in reality. So I started to implement it in a certain way, and it turned out that it doesn't work that way. So I re-implemented it in 3 different ways until I found a way which really works well on Linux computer clusters and supercomputers without crashing the entire computer cluster. And yeah, this was one of the major challenges in the beginning. Other challenges which we are facing are, for example, when we need to experimentally verify what we have computationally discovered, like in the lab. Yeah.
Got it. Okay. So in terms of these challenges, I remember on our previous call you kind of mentioned this, but it sounds like Google Cloud has really been able to be a big tool in helping to find solutions. Maybe tell me a little bit more about that in your own words. How has Google Cloud been able to help you overcome some of these challenges and problems and get to those solutions faster?
Yeah. So yeah, Virtual Flow was first implemented to run on any type of supercomputer or Linux cluster. And when we wanted to port it to the cloud, we started to engage with some people at Google, and they provided us with a tremendous amount of support to really upscale the computations there. So it's not difficult to run Virtual Flow in the Google Cloud because the Google Cloud provides a Slurm cluster which runs on the Google Cloud, and Virtual Flow runs on the Slurm cluster. So technically it's not a problem, but what was very challenging was to scale up the computations in the Google Cloud to hundreds of thousands of CPUs. And there we got a lot of help from Google to make this work. Yeah.
Right. And I remember you mentioning that on the pre-call too. There was this moment where you didn't know if it could handle the system. Kind of walk me through that when, and then how you came to solutions around that.
Yeah. So, when we started to upscale the computations in the Google Cloud, the amount of I/O operations also increased with the number of CPUs. And the file system was initially not powerful enough. So Google pointed us to the right file system which we needed to use, which was Elastifile Cloud File Service storage. And this file system was able to handle all the I/O which we needed and solve the problem with that.
That's great. So it sounds like Google has been a really great partner and collaborator. You know, going forward into your future projects, do you think you will continue to partner with Google?
Yes, we will absolutely continue to partner with Google. Google was an amazing collaborator so far. They have provided us an incredible support to make Virtual Flow run, and also to apply it to COVID-19 to discover new drug candidates for this disease. Yeah, and we are planning to continue to work with Google on several projects, and we are super excited about this.
That's great. And, you know, in terms of COVID-19, tell me a little bit more for people who aren't familiar with Virtual Flow how virtual flow can be a tool for solutions around COVID-19.
Yeah, so the COVID-19 virus, SARS-CoV-2, consists of different components, and many of these components are proteins of the virus, which play a critical part in the life cycle of the virus. So when we want to disrupt the life cycle of the virus in cells, then we can do this by finding the proper small molecules which bind to the proper sites of these of these proteins to disrupt the functions of the virus. For example, there is one protein, the spike protein of the virus, which binds to human proteins on the surface of the cells called ACE2. And the spike protein recognizes ACE2 and binds to ACE2. And once it has bound, the cell takes the virus into the cell. And when we find, for example, a molecule which binds to the spike protein, then it would prevent that it binds to ACE2 and thus to enter the cells.
That's great. Wow. So like back to the beginning of virtual flow and how you first got started, take me back to when you first met Hari and, take me back to when you first met him, how you met him. And then also he shared, how when you two first met, how you told him, what if I could tell you I could screen billions of molecules? So kind of take me back to those first moments and how you both connected.
Yeah, so in my PhD, I started to work on my own drug discovery project, which involved a protein which plays a role in cancer. And I applied virtual flow to it, and I was looking for someone who could verify experimentally the results. So I found Hari here in Boston, and I asked him if his group could verify these results. I told him I screened 100 million compounds, and you need to check if the results are really true. And then Hari said he was quite impressed, I think, that it's possible to screen so many compounds. And he told me that for their own drug discovery projects, they screened around 200,000 compounds or so. And he asked me if I could apply virtual flow to their projects to find better compounds. Yeah.
Can I briefly jump in, Tasha?
Definitely.
I'm curious you're talking about really cutting edge technology but you speak about it so humbly. And I wonder, is there anyone else in the world that has been able to achieve the level of, drug testing that you're talking about? Or is virtual flow the only program out there that can do this?
So there exists a number of other approaches and software, but as far as we know, none is comparable to virtual flow. So there are other virtual screening platforms which can screen smaller number of compounds. And there are other approaches. There might be one or two approaches which have demonstrated to screen 1 billion compounds, but it's more based on AI, and I'm not completely sure right now if this can be applied to any protein. I think I saw one approach which needed to be trained specifically for each target, so it couldn't be applied straightforwardly to any protein. But I would need to verify this before you air this. So
I was mostly curious. But
yeah,
go ahead, please.
There's one company called Schrödinger. On their homepage, they mentioned that they also can screen billions of compounds, but they only do shape-based screenings at the moment. So they only take into account the shape of the molecule rather than the complete interactions of the molecule with the protein. So it would not be useful in many cases. I wouldn't add this either because I don't want to talk